Hi, good morning. Just to recall what we have discussed in our last class. We have discussed the definition of ideal and some examples of ideal, then the definition of maximal ideals. Okay, now what do you mean by a maximal ideal? A maximal ideal M of a ring, a maximal ideal of a ring R is an ideal M different from R such that there is no proper ideal N of R properly containing M. Okay, now we are going to one of the most important theorem, and the theorem says that let R be a ring with unity. Clear? Listen carefully, this is most important theorem. Let R be a commutative ring with unity. Then M is a maximal ideal of R if and only if R by M is a field. If and only if R by M is a field. So once again we are moving to definition of maximal ideal. A maximal ideal of a ring R is an ideal M different from R. So if M is a maximal ideal, then clearly M must be not equal to R, and there does not exist a proper ideal of R properly containing M. That is, there does not exist a N such that M is properly contained in N. Okay, then we call M is a maximal ideal. And the theorem says that if R is a commutative ring with unity, M is a maximal ideal if and only if R by M is a field. Clear? So M is a maximal ideal means if and only if R by M is a field. So we are proving the first part. Suppose M is a maximal ideal of R and we have to prove R by M is a field. To prove R by M is a field, what we have to prove? As M is a maximal ideal and as R is a ring, we know that R by M is also a commutative ring. R is a commutative ring with unity, therefore R by M is also a commutative ring with unity. And to prove as R is a commutative ring with unity, R by M is also a non-zero commutative ring with unity. So to prove R by M is a field, what we have to prove? We have to prove every element of R by M is a unit. Okay. So what do you mean by a field? A field means a commutative division ring. Now what do you mean by a division ring? If every non-zero element is a unit, then we call that ring as that is a division ring. So we have to prove every element of R by M is a unit. So as M is a maximal ideal, clearly M not equal to R. That means, what is the meaning of that? M is a subset of R and M is not equal to R. That means there exists A belongs to R such that A not belongs to M. You can find A belongs to R but A does not belongs to M. Now for this A, what is A plus M? We have a result, if A belongs to H, then AH is equal to H. Or in general, if A not belongs to M, then clearly A plus M is not equal to M. Okay, that means A plus, what about the identity element in R by M? What about the identity element in R by M? We know that if G over H, if you consider this identity element, what about the identity element? H is the identity element in this group. Okay. Similarly, M is the identity element in R by M. This consists of elements of the form A plus M. Okay. So, A plus M is not the identity element of R by M. So A plus M is not the identity element. What about what is the meaning of R by M is a field? We have to prove every non-zero element. What is the meaning of every non-zero element? That means every element other than identity element must be a unit. So here A plus M is not an identity element. That means A plus M, we have to prove that A plus M has an inverse in R by M. Okay, so we are going to prove A plus M is not an identity element and we have to prove A plus M has an inverse in R by M. So we are assuming the contradiction. Suppose a plus m has no multiplicative inverse in r by m. Once again I am repeating, we have to prove r by m is a field. Okay, to prove r by m is a field, it is enough to prove that r by m is a commutative division ring. As R is a commutative division ring, clearly R by M is a non-zero commutative ring. To prove it is a division ring, we have to prove every non-zero element of R by M has an inverse in R by M. Non-zero means, zero means identity element. In R by M, identity element is M. So as A not belongs to M, clearly we have A plus M is not equal to M. That means A plus M is not an identity element. So we have to prove A plus M has an inverse in R by M. As A plus M is arbitrary, we can easily say that every non-zero element in R by M has an inverse in R by M. So for this we are assuming, suppose A plus M does not have an inverse in R by M. Clear? Okay. So if you consider A plus M is an element in R by M, R over M. Okay, so if you consider this as no inverse means, if you multiply this element with any element of this element, then clearly that does not contain a unity. Okay, that means if you consider this set A plus M into R by M, that is equal to A plus M into R over M. The elements of R over M is of the form R plus M, where R is clearly small letter r belongs to capital R. And this set is equal to AR plus M by definition of product. Okay, so this is equal to AR plus M, which is such that R belongs to R. Okay, so as A plus M does not have a multiplicative inverse, this set clearly does not contain the element 1 plus M, because if it has an inverse, A plus M into that element is equal to 1 plus M. Okay, if this, as it is does not have an inverse, means this set does not contain the element 1 plus M. Okay, so we are now choosing n is equal to, A plus M into R by M. Let x belongs to R. Then x plus m clearly belongs to R over M. Then x plus m into n is equal to elements of n are of the form AR plus M, and that's equal to A into Rx plus M, and this is of the form AR1 plus M, and clearly this belongs to n, that is of the form A plus M. Okay, so clearly xn is a subset of n for every x. Similarly, we can prove ny is a subset of n for every. That means n is an ideal as xn and ny belongs to n for every, here for every y belongs to R over n. You must change this, okay? For every y belongs to R over m. Therefore, n is an ideal in R over m. Okay? Clearly, it is non-trivial because A not belongs to m. And it is a proper ideal because it does not contain 1 plus m. Once again, n is equal to A plus m into R over m is an ideal. We have proved this is an ideal. Clearly, this is non-trivial because A not belongs to m. Also, it is proper ideal because clearly we have, by our assumption, that does not contain 1 plus m. That means clearly this is an ideal. And this is a proper ideal. This is contained in R over M, and this is a proper ideal of R over M because 1 plus M does not belongs to this set. Okay. Therefore, A plus M into R over M is a non-trivial proper ideal in R over M. Now let gamma is a map from R to R over M with a canonical homomorphism defined like this: gamma of x equal to x plus m. If x belongs to m, gamma of x equal to x plus m, which is equal to m. Therefore, if we define like this, gamma from R to R over m, gamma of x equal to x plus m. If x belongs to m, then what happens? Gamma of x is, we get gamma of x equal to m. and clearly gamma of R is contained in R over M. Here we get gamma of, if you take any x belongs to M, then gamma of that x is equal to M, and clearly image is contained in R, therefore M is contained in R over M. Okay, therefore what we get M is contained in gamma inverse of, okay, M. So for any subset A of R over M containing the identity, M is contained in gamma inverse of A. Okay, so what about gamma inverse of A plus M into R over M? Is a proper ideal of R properly containing M. Okay, so here what we get, gamma inverse of, we have for any subset A of R over M containing the identity, M is contained in gamma inverse of A. That means if here A plus M or R over M is we replace A by A plus M R over M. So gamma inverse is a proper ideal of R properly containing M. But this is a contradiction to our assumption that M is a maximal ideal, because we assume that M is a maximal ideal, and here we get gamma inverse of A plus M over R over M is, M is properly contained in this set, and clearly this set is a proper subspace of, okay, this set is also a proper subspace of R. That means that is a contradiction, because we assume that M is a maximal ideal. That means all our this contradiction arises just because we assume that A plus M has a does not have a multiplicative inverse. Therefore A plus M must have a multiplicative inverse in R over M. That means every element other than identity element in R over M has a multiplicative inverse in R over M. That implies R over M, R by M is a field. Okay. Now conversely, suppose that R over M is a field, and we have to prove that M is a maximal ideal. If N is any ideal of R such that M is properly contained in N is properly contained in R, gamma is a canonical homomorphism from R onto R over M, then gamma N is an ideal in R over M with 0 plus M contained in gamma N contained in R over M. Therefore, by corollary 1.5, R over M contains no proper non-trivial ideals, because R over M is a field. Therefore, field contains no proper non-trivial ideal. But here we get gamma of N is contained in R over M. That is a contradiction. That means we get gamma of N is a since we get gamma of here square bracket is a proper non-trivial ideal. This implies if R over M is a field, then M is a maximal ideal, because here we assume that M is not maximal, and here we get a contradiction. Therefore, if R over M is a field, then M is a maximal ideal. This is one of the most important results. If R is a commutative ring with unity, then M is a maximal ideal if and only if R over M is a field. Now there is a corollary. A commutative ring with unity is a field if and only if it has no proper non-trivial ideal. Suppose R is a commutative ring with unity. First assume that R is a field. Okay. Then by our proposition 1.5, R has no proper non-trivial ideal. This implies 0 is the maximal ideal in R. This implies R over 0 is a field, R over 0 is isomorphic to R, hence that is R is a field. That is an if and only if condition. Okay. Conversely, suppose that R has, conversely assume that R is a ring with unity that has no proper non-trivial ideal, then clearly, okay, non-trivial ideal, then clearly we get it is a field. Okay, here we get R over 0 is a field, okay. And if R is a field, then also by corollary 1.5, R has no proper non-trivial ideals. Okay. Now find all maximal ideals of set. This is one of the most important problem. Suppose Z is a, we know that Z is a commutative ring with unity. All ideals in Z are of the form nz, and if Z over nz is isomorphic to Zn. If n is a maximal ideal, then R over n is a field. So this Z over nz is a field if and only if n is a prime number. Therefore, maximal ideals of Z are of the form Pz, where P is a positive integer. Okay, that's all for today's class. In the next class, we will discuss about prime ideals. Okay.